Hello my dear students. So this is my 7th video lecture, and today I will discuss about different types of phase diagrams. So basically we have 4 types of phase diagrams. These are: first is eutectic diagram. Then the second one is eutectoid diagram. Third is peritectic diagram, and fourth one is peritectoid diagram. So these are the 4 different types of phase diagrams, and today we shall talk about this eutectic diagram. We shall talk about this eutectic phase diagram. So the eutectic reaction, before starting this diagram, we shall talk about this eutectic reaction. So what is eutectic reaction? Eutectic reaction is L, liquid, on cooling. Cooling means by removing the latent heat, it will convert it into 2 different solid phases. One is alpha, another is beta. So this liquid phase will convert it into 2 different solid phases on cooling, or by heating these 2 separate solid phases, we will get one liquid phase. Here we have one PVSN phase diagram, lead tin phase diagram, which is a eutectic diagram. This PVSN phase diagram is an eutectic phase diagram. So we shall talk about this PVSN phase diagram. So first of all, what is eutectic diagram or eutectic reaction? So I have shown you that eutectic reaction, that was this is the eutectic reaction. Here we have 2 different solid phases, alpha and beta, which are totally or partially insoluble in solid phase, but totally or completely soluble in liquid phase. So these 2 solid phases, these are partially or completely insoluble in solid phase, but whenever we will convert it in liquid phase, so these 2 will completely soluble in that liquid phase. So now we have this eutectic phase diagram, which is a PVSN phase diagram. So in this diagram we have 4 different colors line. two blue lines, two red lines, one purple color line, and two green line. So these two blue lines, these are liquidus line. You know about this liquidus line? So these blue lines are liquidus lines. And we have two red lines, these are solidus lines. These are solidus line. And one purple color line, this line is tie line, where we have constant temperature, or this is isothermal line. And now this one, this is called Solvus line. So in my previous classes, I have already told you about this liquidus line, solidus line, and tie line. So now you have to know about this Solvus line. The Solvus line is a line which separates a solid phase from two phase region, but this two phase region must be consist of two different types of solid phases. So these Solvus line are separating a two phase region from two different solid phases, and we have alpha plus beta in this place. In this two phase region, we have alpha plus beta, two different solid phases. So this Solvus line is separating these two solid phases from this two phase region. Or we can define it as the Solvus line represents the locus of solubility limits. This line is the locus of solubility limits for the solid solution in a multi-component system. So the system should be a multi-component system. So this is the definition of Solvus line, or you can say the Solvus line, we can define it as, for this one, we can say this is the solubility limit of Sn in PV. So Sn or tin can be dissolved in PV led up to this solubility line, or this PV can dissolve in Sn up to this Solvus line. So these lines are the solubility limit of two different components. Now I have told you about this table in my fifth video lecture. Here in this case, in this Eutectic diagram, we have three different phases. Two are solid phase, this alpha and beta, these two solid phase, and one liquid phase. So we have three different phases. So if we have three different phases, by using this formula, V is equal to P into C minus 1 plus 1, by using this formula, we can get the number of variables is equal to 4 by putting the value of P is equal to 3, and C is always for binary system, C is equal to 2. So we have 4 different variables. So what are these 4 different variables? 3 composition variables, and 1 temperature variable. So thus, by putting this value in this formula, we can get the degree of freedom is equal to 0. So how we have 3 composition? We can see here we have composition C beta, here we have composition C alpha, and here we have Cl. So we have three different composition variables. These are C alpha, C beta, and Cl. So these three are equilibrium along with this tie line. Up to this point, beta phase is in equilibrium. Up to this point, alpha phase is in equilibrium. And up to this point, liquid phase is in equilibrium. So along these tie line or isothermal line, we have three different compositions are in equilibrium. So here this is not a simple type of phase diagram like that Copernican diagram, which was an isomorphous system. So this is the reaction, eutectic reaction. So here we have written cooling and heating. This cooling and heating does not mean lowering or increasing the temperature. Here we are adding, heating means we are adding the latent heat, and cooling means we are removing the latent heat. So by cooling, we can change the state from liquid to solid, and by heating or adding the latent heat, we can convert this solid state into liquid state. Let us take one example. So we can take the example of ice at 0 degree C. And after adding the latent heat at same temperature 0 degree C, ice melts and converted into water. Or we also can say at 0 degree C, by removing the latent heat from the water, it will converted into ice. So here it is just same. In this case also it is just same. By heating these two different phases, we are converting it into liquid. In case of water and ice, we have only two different phases. One is water, another is ice. But here we have three different phases. So the water, when we have removed that latent heat from water, that has been converted into a single phase, that is ice. But in this case, as these are not soluble in each other, so these converted into two different phases. One is alpha phase, another is beta phase. I think you know about the difference between phase and state, which I have already discussed in my previous lecture. So this eutectic reaction is also known as invariant reaction. Invariant reaction. So this eutectic reaction is also known as invariant reaction. Now we will see the different microstructures at different temperature. So here we have PVSN phase diagram. In this side we have composition, and this side we have temperature. So this temperature, constant temperature or tie line, it is 183 degree C. So we have drawn this tie line at 183 degree C. So now we will see the different microstructures. Here we can see this point is, the composition of this point is 80.5% of lead and remaining 19.5% is Sn. So these C beta is consist of C beta is consist of 80.5% of PV and 19.5% of Sn. And here at eutectic point, this point is known as eutectic point. At eutectic point, the composition is 62% of Sn and remaining 38% of PV. And here we have alpha composition C alpha, where 2.6% of 2.6% of PV and remaining 97.4% of Sn. So I already told you these green lines are solubility limit. So now this microstructure, we will draw the microstructure at above of the temperature above of 183 degrees C, means let us say in this point. So in this point we will have all liquids. So the microstructure will be like this at this point where we have only liquid phase. And at that eutectic temperature we will have continuous layer of two different phases, continuous layer of two different phases, alpha and beta. So these are continuous alternative layers of alpha and beta. Let's say this is alpha phase and this one is beta phase. So at eutectic temperature we have continuous alternative layer of alpha and beta like this one. So now just below this liquidus line, just below this liquidus line, like at this place, at this place we will have some globular form of beta like this. In this place, as in this place we have a beta rich region, and like this is consist of beta and liquid phase. So these are beta and these sky color dots are liquid phase. Now I shall draw for T is equal to 183.1 degree C, means just above this line, So here we have some globular beta this is in very less number, and combination of alpha and beta so these red places are combination of alpha and beta. So in this case we have two different kinds of beta. One is globular, another is this crystal. So these crystals are combination of alpha and beta. Like this. So this is just above this, like in this place, just above this tie line, 183 degree C. So here we have two different regions. One is hyper-eutectic region, another is hypo-eutectic region. So up to this 62 degree, up to this 62% of that PV, we have hypo-eutectic, and this side we have hyper-eutectic. So up to this line, 62% of SN, we have a hypoeutectic, and after this 62% we have hypereutectic region. So these two region we do have in this place. Now we have two types of eutectic diagram. One is two metals completely soluble in liquid state but partially soluble in solid state. So this is this kind of diagram where the alpha and beta, these are partially soluble in solid state. But we have another kind of eutectic reaction where these the solid phases are completely insoluble in solid state. This one here, the alpha and beta are totally insoluble in solid phase. So here we have little bit solubility or partial solubility in solid state. So that's why we have this Solvus line, as these alpha and beta are partially soluble in solid phase, but in this case we don't have any Solvus line in this place, as these are completely insoluble in solid phase. So here these are the different microstructures at different place. So this is at this place where we have only liquid phase. So as we have liquid phase, that's why this consists of only liquid phase, and this is below the liquidus line where we have liquid plus alpha. Here the liquid is converting into alpha phase. So by removing the latent heat, that's why we have these two phases in this region. So this is the microstructure at this region. Here we have this place is tin rich solid. This region is tin rich solid. So this is solid, and this is the remaining is liquid. So here we have eutectic plus alpha. In this side, as we have in this side we have alpha phase, in this side we have alpha phase, and this side we have beta phase. So if we take this region, which is hypereutectic region, we have maximum number, or we have some more amount of alpha phase. That's why this core is alpha core, and we have remaining is eutectic, alpha plus beta. So at eutectic we have both alpha plus beta, which is consist of 38% of Pb and 62% of Sn. So this is the solid structure of eutectic region. In the previous sheet also I have shown you the like this. So this diagram and this diagram, these two are same PV-SN diagram. Just I have flipped it. In this case I have flipped it. Here in this case Sn is this side, PV is in this side, and here Sn is this side and PV is this side. That's why for this case alpha is in this side and beta is in this side, and here alpha is in this side and beta is in this side. So if we take hypoeutectic region, in this region we have beta plus eutectic mixture. So this is beta cold and remaining is eutectic. structure. And if you take between this tie line and this below this liquidus line, so this will like this. So from this figure we can say tin is dissolved up to maximum 2.6% of PV at eutectic temperature. 2.6% of PV. Tin will dissolve up to 2.6% of PV at eutectic temperature. This is the eutectic temperature, which is 183 degree C. And lead will dissolve up to a maximum 19.5% tin at eutectic temperature, giving the solid solution beta or beta phase. So this is one type of eutectic reaction where we have total solubility in liquid state but partial solubility in solid state. Now this is the second case where total solubility in liquid phase but totally insoluble in solid state. So this point is A point, and for this A point we have this microstructure. So this is cadmium bismuth, cadmium bismuth, cadmium or cadmium bismuth, bismuth cadmium phase diagram, which is consist of bismuth and cadmium. These are practically, we don't have any this kind of diagram which are totally insoluble in solid phase, but the amount of solubility is very less. That's why we are taking as or considering as totally insoluble in solid state. So that's why we don't have any Solvus line in this case. So at A point we have liquid plus bismuth. As we have in this place we have bismuth rich region. So that's why A point is consist of liquid plus bismuth, and the microstructure is like this, liquid plus bismuth. So this point is just below this liquidus line. That's why liquid phase is maximum and little amount of bismuth has been converted into solid phase. Then point B. This is the point B where we have eutectic plus bismuth. So these are bismuth and these are eutectic. We have maximum number of eutectic and little bit of bismuth, as this place is bismuth rich place. Then eutectic place, this is eutectic region. This is liquid plus, this point is liquid plus cadmium, and this one is cadmium plus eutectic. So that's all for today. Thank you.